Let's talk about how buffers work. If we take an ethanoic acid here, this is a weak acid. Any weak acid will work, but this is ethanoic acid. It will dissociate to form ethanoate ions and H plus ions, and this is in equilibrium. That's important. When we neutralise a strong acid, we get a reaction which produces a salt and water, but that's not in equilibrium. That just reacts all the way. The equilibrium gives us an effect that we call buffering when we add sodium hydroxide. So if we add sodium hydroxide, we're going to get the same reaction that we would expect with a strong acid. We're going to get the H plus and the OH minus are going to neutralise to produce water, which you would imagine means that we are using up the H plus, and you would expect if there's a concentration of H plus is going to go down, you would expect the pH to go up. But that's not quite what happens here. Because we are using up the H plus, this equilibrium here, according to Le Chatelier's principle, is going to shift to counteract the change. So it's actually going to shift to the right in order to regenerate the H plus. So what that means is that as you add NaOH, even though you're adding an alkali to the acid, because there's a lot of this still left over, about 99% of the ethanoic acid solution is undissociated ethanoic acid. As it shifts right, the concentration of ethanoic acid itself will go down. The concentration of the salt will go up as this reacts. And because we are using this up in the second reaction here, and then it is being generated by the equilibrium, the concentration of H plus actually stays more or less the same as it was. Now, it will decrease very, very slightly, but not anywhere near as much as you would expect. And therefore the change in H plus concentration, and therefore the change in pH, is very minimal when we add sodium hydroxide solution. When we have added enough of the sodium hydroxide solution to use up all of this acid, the buffering effect stops. And the buffering effect stops because there is no more of this. It's gone. The equilibrium cannot shift anymore. So the concentration of the salt is now going to be constant, and the concentration of the H plus will now decrease. So the buffering only works to a certain extent until you've used up your reserve of weak acid. Let's now have a look at what would happen if you had a solution of sodium ethanoate, something which contained just the ethanoate ions. If we had ethanoate ions, they would react with H plus from the water to form a small amount of the ethanoic acid. So it would still be in equilibrium, but this time we've got a lot more of the salt compared to the acid. So if we took that solution and we added HCl, then we would see a different but similar effect. So what's going to happen now is as we add HCl, we're going to increase the concentration of H plus. And when we increase the concentration of H plus, that means there's much more H plus here. The concentration is higher. Le Chatelier's principle tells us that the reaction is going to shift to counteract the change. It will go this direction this time. And so the additional H plus is going to react with the salt, and it will form the acid on the left-hand side of the equation. And overall, what that means is that the concentration of the salt is going to go down. The concentration of the acid is going to go up. And as we add the H plus, it is used up. And therefore, once again, the concentration of H plus stays more or less the same. It's going to go up very slightly, but mainly it's staying round about where it was before. Minimal change in the H plus concentration. And so this is having the same effect in the reverse direction. As we add the HCl to our sodium ethanoate, the pH is not going to drop suddenly, like we would expect when we add acid to a solution. It's actually going to stay pretty constant, reducing very, very slightly up until the point where we have used up all of the salt. At the point where we've used up all of the salt, the equilibrium can no longer shift to the left. All of the salt has been made into the acid. This can no longer change, and therefore the H+ concentration no longer stays more or less the same. The addition of excess acid is going to force the concentration of H+ up, which means that you will get the change in pH. So a buffer solution is a solution which contains both of these two species, a weak acid and its conjugate base, or salt. So in that case, we have plenty of weak acid, so that if we add a small amount of NaOH or another alkali, then we will be able to shift the equilibrium to the right to minimise the change in H+. And if we have enough of this in the solution as well, then if we add a small amount of acid, then we will cause the equilibrium to shift to the left. So it doesn't matter whether it's alkali or acid. If we've got a reserve of each of these in solution, then the pH change will be minimised, regardless of whether we add a small amount of acid or a small amount of alkali. That's limited to the amount of acid or alkali to use up the reserve of either the acid or the salt. So what a buffer does as a description is it minimises the pH change when small amounts of acid or alkali are added. In terms of choosing a buffer then, if you wanted a certain pH of a buffer, we would have to look at this equation. The acid dissociation constant Ka of a weak acid gives us, as this expression here, the concentration of H+, concentration of the salt in the buffer solution, the concentration of the undissociated acid. Using the Ka value, we can work out what pH buffer would be suitable for, because the best buffer is going to be when the acid and the salt are in equal quantities. That will buffer the solution each way by the same amount. And so therefore we want the ratio of A minus and HA, that's these two, to be 1 to 1. And if we substitute 1 and 1 in there, we can give the equation Ka is therefore equal to H+ when we have a 1 to 1 ratio of acid and salt. Okay, so this only applies when we've set up our buffer with the same quantity of each. If we take the minus log of each side, we end up with this expression. The pKa is equal to the pH of the buffer if you have a 1 to 1 ratio of salt and acid.
The pH the buffer works best at then is the same as the pKa, but we can manipulate the concentration of each of these chemicals to manipulate the pH, make it higher or lower. The ratio of these changes, that would make the pH change as well. So if we want to know the limit of that, generally speaking, we say that if this is a 10 to 1 or a 10 to 1 ratio, that's the limit of where we get useful buffering. That means that when we use this equation, we can, for this particular acid, we can look at the pKa. The pKa is 4.76. And when we have a 1 to 10 or a 10 to 1 ratio here, that would change the pH by up to a value of 1 each way. And so the useful range for this buffer would be 4.76 plus or minus 1 pH unit.